Thanks, Robbie, and thank all of you for coming out today to see this talk. It's a real privilege and a delight to be able to talk to this audience. ICFP has been an intellectual home of mine for quite a while. I've gotten a lot of ideas from here and made a lot of friends, and I'm really looking forward to this chance to talk to you about my perspective on gradual typing, which I've been working on for about 10 years or so now with a lot of other people. It's a nice research community. So I'm going to start off with the basic gist of gradual typing, which you may have the idea of, but I'll just start there, which is to say that there's been this long-standing divide between languages that try to check program properties statically and those that check them dynamically. And what often happens is the static, people who prefer static, really enjoy the ability to detect errors early before they even run their programs, and also enjoy the discipline that's imposed on them by aspects of type structure. On the other hand, in the dynamic world, dynamic language aficionados really appreciate being able to quickly get to rapid prototyping of an idea that is, half or maybe 1/4 baked, but then at the same time enjoy the ability over time to experiment with and exploit flexible idioms that the languages allow them. So gradual typing is really this effort to combine the benefits of both of these vantage points into a single language and be able to allow a programmer-controlled migration between both disciplines, enjoying both benefits simultaneously. So that's really gradual typing. And in this talk, what I'm going to do is try and flesh out those ideas a bit further, at least from my vantage point. And I'll do it in several parts. So first I'll give a motivating example, and then I'll talk about how gradual typing is for all. We'll talk about typing in small pieces. I'll give you some meat, and then we'll talk about some strands and related works. So first, let me give you some motivation. To do so, I'd like to talk a bit about a dynamic language that has been well studied and appreciated in the ICFP community, and that's standard ML. So standard ML was developed by as part of, it came out of Ronald's work, where he developed ML as the meta language for the LCF theorem prover and used it to write tactics. And as is often with domain-specific languages, it turned out this language was really useful. So several implementations later that happen to not work with one another, there's a need for a standardization, and you end up with this language. So standard ML, and you know that it's dynamic. It's a dynamic language. You have to look no further than its algebraic data types, which allow you to do things like encode the natural numbers as being 0 or the successor of your natural number. And then you use this case mechanism to dispatch and figure out whether you have a 0 or a successor. So the standard requires that you be able to accept non-exhaustive matches. So for instance, this case statement here just takes just checks to make sure if it's a successor and then keeps going. But if F is 0, if for some reason you ended up passing it there, an exception match is raised. So yeah, dynamic type error, dynamic language. So the non-exhaustive match is fine as long as you know that anything that's substituted into X is going to be 0. So just make sure that you don't ever pass 0 in, and you're okay. Well, people who like static types don't sleep well at night thinking about that kind of thing. So, they'd say like, we really and we have to find a way to tame this dynamic language. And someone was willing to rise to the occasion. So when he was busy inspiring the next generation of computer scientists, Frank Fenning and his students were working on developing the 12th theorem prover, which was implemented in standard ML. So standard ML was its implementation language, not its meta language. And it's a pretty substantial code base, and he had a lot of experience with standard ML and these non-exhaustive matches. And he came to observe that non-exhaustive matches are a widely employed style of programming which imposes no discipline of types. And he had to relent and say that such flexibility is almost essential in this style of programming, and unfortunately one often pays the price for it in the time taken to find all these inscrutable bugs. So I wasn't there at the time that Frank was developing this work or thinking about these ideas, and yeah, I lifted these comments from Milner, who might have been talking about Lisp. But I think it really captures the spirit of what he was thinking about in this case, in this situation. So working with a really amazing group of graduate students that led to a succession of really fascinating theses, Frank and his students developed this idea of data sort refinement or type refinement, which allows you to refine the types of your algebraic data types to allow, say, non-zero to be pushed through the source code so that you can statically guarantee that this particular case is in fact exhaustive, even though it doesn't have all of the arms. So, problem solved. Types people happy. Or are they? Stay tuned. So, let's talk a little bit about adoption. So the TIOBE index is this webpage that tries to evaluate the popularity of various programming languages and then order them by rank. So if you go to the website and then you work your way down and look at it, you'll find like, okay, there's ML among the next 50 programming languages. Yeah, that's better than the next 700. Turns out that, oh, look, there's Scheme up above ML, just where we expect to find it. But it turns out there's no refined ML on this page. So if you take a little time to think about it, the scientific investigation tells you that it's likely that there's a lot less refined ML code in the world than there is standard ML code in the world. But as a fan of types, I want to enjoy the benefits of static type checking. So what I'll do is I'll take my old applications that are written in standard ML and then migrate them to refined ML. And in the process, I may find some bugs thanks to my new type checker, or at least I'll sleep better at night knowing that a whole new class of bugs is guaranteed not to exist compared to the ones that were guaranteed not to exist before. So if I try to repeat this process, then sometimes I'll find that, oh, this application relies on this other library. So we run into a situation that calls for wholesale migration. So it turns out like a static type system and typed programs have a lot in common with load-bearing architecture, kind of like an arch. So an arch is a really fascinating structure because it distributes the weight pretty evenly so that it's very stable structure, but if you pop a part of it out, the whole thing's going to come crumbling down, so you really have to make sure that the thing is fully built and scaffolded before you complete it. So we'll deal with this migration, and first I'll migrate the library, and then I'll finally migrate my whole application and enjoy the same benefits as in my last effort. But now suppose that library 1 in standard ML is really useful, and I want to use it, or library 2 is useful in my applications, and I'd like to use it from refined ML. And maybe I'm not sure if it's exactly the right thing, but it really seems helpful. And it'd be really unfortunate if I really had to just assimilate the entire library into refined ML before I could even do any experimentation. There's really got to be a better way. So wouldn't it be nice if there was some way to gradually migrate this code over into refined ML and then be able to directly link against it and enjoy the benefits of at least either experimentation, and maybe later I could decide to transform this code into refined ML. So if we think about it, we're in this situation where we have a code base that now has two different kinds of code, standard ML code and refined ML code, and two different kinds of guarantees, those podunk standard ML guarantees and the really nice, rich, refined ML guarantees. So we have to stop and think about, is this even going to work? So in the case of the standard ML guarantee, it's like, well, yeah, they were pretty weak in the first place already, so it's reasonably safe to say that we could just wipe away all of our nice guarantees in our refined ML code, maybe just, put refined ML type annotations in comment notation in ML or something like that so that your compiler understands them, but then doesn't, and then you just compile it using the standard ML compiler. I hear the kids these days call this optional typing. But then on the other hand, we have to consider, what about the guarantees of the refined ML type system, the thing that we know and love and really wanted to appreciate? So things get more complicated here. And the reason is that there are behaviors in the standard ML code that might violate the discipline of the refined ML and can kind of pollute its semantics and the guarantees that we enjoy. So somehow we have to find a way to contain the infectious behavior of the standard ML code. And that's the challenge in this situation. Lucky for us, there's people who've been thinking about this, and at last year's POPL, there was a paper that was just making the first beginnings at trying to make gradual typing a reality. Interestingly enough, the second author on this paper, Joshua Dunfield, was indeed one of those grad students who produced a PhD thesis that helped develop the theory of refinement types in the first place. So what a twist. Gradual typing for all. So, I've been talking to you about the wonderful idea of moving from the dynamic world of ML types to refinement types and trying to explain that refinement types will make your life better. But did you know that there are people who program in languages with type systems that are weaker than MLs? So really, the way I think about this is it kind of reminds me of the XKCD comic where you have fields arranged by purity, but instead what we're really doing is talking about languages that are at least partially ordered by typedness. And so we can take the bold move and decide that we'll transport the idea of gradual typing from going from ML types to refined types to maybe moving untyped languages over to ML types. That'd be pretty cool too, I guess. And you might even say well, forget this ML stuff. It's already too weak for us. Let's just go straight by from untyped to refined ML and wave hello as we pass overhead. So the key concept here is that gradual typing is a relative notion. I think it was best said by a well-known non-serial killer in our community who made the observation that, I always assumed gradual types were to help those poor schmucks using untyped languages to migrate to typed languages. I now realize that I am one of the poor schmucks. So is Phil in the audience? Hey, Phil, you are a schmuck. And you make it every day, I don't know, but thank you. So seriously, most work on untyped languages, most work on gradual typing is done from untyped languages to ML or richer type systems. And you usually have your dynamic language, maybe like in this scenario, and then your static language. But more recently, there's a lot more work that's trying to go from types to be typier. And in that case, the thing that you call a dynamic language isn't typically what gets argued about as being dynamic on the internet, at least. And the internet's always right. Crowdsourced intelligence. So let me talk about types in small pieces. So when I tell someone about gradual types, sometimes they're like, gradual types? What they're trying to say using inflection is, what does gradual typing have to do with types? So before I get into gradual typing, let's talk about types. So part of the issue with thinking about this is we really have to try and take seriously the idea what are types about? What does it really mean? And if you came up in my era, this is probably the answer that you had, where you'd see a typical instance of a type system, and it would look something like this. And this thing here is it's an inductive definition, which is another way of saying that it's a grammar on steroids, which means it's a specification for a data structure, where the data structure is the derivation trees that you can build using these constructors. And one of the important notes about this is that it's really it's informally ascribed behavioral meaning. So if you show this to a non-expert, they might be like, huh. Or true story, I was writing down something that looked like this, and my mother-in-law was like, that's kind of beautiful. Can you give me one of those so that I can put it into some of my artwork? And I was like, it is beautiful. So Nobel-winning, prize-winning psychologist Daniel Kahneman has this saying in his book Thinking Fast and Slow, where he says, if you're shown a word on a screen in a language that you know, you will read it. And what he means by that is that if you come down here and look at this data structure, we implicitly ascribe meaning to all of the letters in here. If I replace them with other things, it would look like noise. But when I look at this, what I see is, lowercase t's are terms and uppercase t's are types. And if T1 turns T11s into T12s and T2 yields T12s, then appropriately linking them will yield T12s. That's kind of like, you just can't help but see that. It's like, oh, look, like the simply typed lambda calculus. It just like pops into your brain before you realize that you took this step. Now, if we're doing formal theory, we try to go a little bit further at least, and then we prove a theorem about it that really connects our data structure to kind of something about operational behavior. And typically it's type safety, where we say, if you have a closed term that's typed, it'll run, and if it runs, then it keeps its type. And this is kind of informally described as, well-typed programs don't go wrong or don't get stuck. So when we transfer this technology over to gradual typing, we have to ask, does gradual typing make sense? And you find that now you've got two problems, where you have two typing judgments, and they really correspond to two, to steal a term of art, behavioral contracts. Whereas we were thinking about, I described the other thing as if-then, but really we're kind of thinking about them as like, one person has to do something, and then I guarantee the other person will do something else. So we're switching from like just a neutral if-then statement to like, no, you must do this and you must do that. But I've already talked about this idea of there being like the possibility of conflict and pollution, and that we need conflict to prevent runtime errors. And so the question then arises, I thought you said well-typed programs don't go wrong. Like, is having this runtime error an instance of going wrong? And there's this question of like, what counts as appropriate linking in between these two things? Like, I have to figure out what's behind the mask, or really I don't care about what's behind the mask. I want to know what is the mask. So to investigate this just a little bit further, I'm going to draw out a bit more the interpretation that we get from these types, from these typing rules. And it's not just the behaviors, but we also have to consider context, which is that there's these gammas floating around that kind of describe what happens in the rest of the program, what's allowed to happen in the rest of the program, not just what a piece of code does. And so really the typing judgments are somehow about program fragments. They're not necessarily talking about whole programs as written. So context matters. And if you go back and look at your type safety proof, you see that that proof is kind of stated to talk about entire programs. It's talking about a property of programs, whereas we're worried a bit about what's going on with these two program fragments in two different languages with two different typing disciplines. So this leads to some trouble just to process. And an observation that I was thinking after thinking about this for quite a long time is, instead of asking whether well-typed whole programs go wrong, I think we should ask, do program fragments go right? It's like, what's that? So pause a moment just to see, like, yeah, we're still where we are. We haven't made a lot of super forward progress. We're talking about types in small pieces, by which I mean fragments. Sorry. That's how this is a Canadian bus. So let's get back to it. So the question is, do program fragments go right? And then we wonder, like, how do we ask this question? And for that, I'm going to go back to my man Milner, who, in the paper where he introduced the ML type system, he talks about this idea of semantic soundness, and a semantic soundness theorem. And translating it into modern notation, we have the typing rules, the typing judgment that we know and love, which is this data structure. But then there's this other thing over here, which you call kind of a semantic judgment over the same things. And it's really, on one hand, you have a thing that's really a data structure, and on the other hand, you really have a behavioral invariant. It kind of corresponds to the intuitive bubbles that I was putting up on the other slide. And indeed, it's like, you're relating your syntax, your data structure, to a formal semantics of behavioral invariance for program fragments. And what this statement of soundness basically says is that every proof of type assignment in your data structure says something meaningful about the positive behavior of a fragment of code. So now at least we can go from our human ability to very quickly impose meaning on something into something that's kind of formal, but we really want the two pieces. So on the right, we now have this idea of modular reasoning about program fragments, our semantic typing judgment. But the one on the left is also important because what it gives us is compositional reasoning principles. We have a set of rules that tell us if I know something about a program fragment and I know something about another program fragment and I know how to appropriately link them, then I know something about this new bigger program fragment that isn't necessarily a program. So both of those together give you this kind of like, you got two daggers that you can go in with if you want to be violent. It's like you've got two lollipops that you can give to the children. Then finally, he gets to the corollary where he wants the big whole program payoff, which is to say that well-typed programs don't go wrong since wrong doesn't have a type. Now, as someone who tends towards the pedantic, I have to note that his abstract is a big fat lie, because he said that the soundness theorem states that well-typed programs don't go wrong, but it doesn't. It implies a corollary that says that well-typed programs don't go wrong. And I think it's useful to take a step back and think about the theorem that was proven, not its lovely corollary, which is that well-typed program fragments go right with respect to your behavioral invariance, which then implies that the whole program doesn't go wrong, which is also a useful thing. So Derek Dreyer, who's also in this community, he gave a talk about some of these ideas of semantic soundness in the context of doing verification in programming languages, and this Popple talk is really a must-see. I think he does a lot more with the story, and this idea of semantic soundness really got picked up in the community and kind of had this sort of parallel track with progress and preservation, in that like the New Perl group at Cornell was using it for working on building proof assistants, and that's kind of migrated into this notion of what's now called computational type theory. And then the foundational proof-carrying code group at Princeton used these techniques to work on how do I type check code without a type checker, basically. And then that work has led into even today's work on the science of deep specification. So there's kind of these two things going on in the world, and they're both really interesting to know about. So I want to take a moment to reflect on progress and preservation and emphasize that even though I'm talking about this idea of program fragments and that progress and preservation seems to be phrased about whole programs, let's not throw the baby out with the bathwater. So our notion of progress and preservation originally comes from this paper by Andrew Wright and Matthias Felleisen, where they introduced this idea of, roughly speaking, like faulty programs don't have types, and programs that have types step in. If they do, they maintain their types. And then Bob Harper came along and kind of flipped around one of these, and that's where you get our progress and preservation as we know today. So, but you dive into the paper, and you find a part at the beginning where they're really, right at the beginning, they're talking about evaluating whole programs and them not going wrong, just as Milner described. And they note that the primary goal of our type system work is to prevent type errors. But then they're like, oh yeah, by the way, we happen to notice that there's this stronger property that relates to the answer produced by the type of the program. So not only does any arbitrary program of any arbitrary type not go wrong, but the type gives you more than Boolean information about like not wrongness. It's like, oh, like yeah, and I know something about the final result. So a little bit of stuff about a program going right. And then to take it even further, in many of the type systems that you would work with today, you can recover the idea of soundness of fragments as a corollary to your typical progress and preservation proof. That's to say, you can build a sort of semantics of your types and then prove that this safety proof then leads you into a soundness fragment using this proof technique. So Milner went from fragment to whole, and Wright and Felleisen allow you to go from whole to fragment, though they were particularly interested in whole, so why would you keep going? Milner just kind of skipped in the abstract, and he's like, no, don't worry about that, really, the theorem. Just like pay no attention, look at the corollary. So I think these observations have some bearing on the gradual typing problem, which is to say that we can take our notions of syntactic thinking and at least change our minds and start thinking about what are the semantics of the particular type systems that I'm trying to blend together, which is to say, what is the semantics of my podunk standard ML? What's the semantics of my wonderful refined ML? And how can I think about preserving go-rightness in the face of linking? Now for some meat. Oh, yeah, I'm vegetarian, so yeah, not so much. And because some of my friends are gluten-free, I decided to accommodate them as well. Which is to say, it's about time I talked a little bit about gradual typing. So whenever you say gradual typing, you kind of have to pause for a second and really figure out when someone's like, yeah, I want gradual typing. And we now, because of its popularity, have to say, well, gradual in what sense? Because there's sort of two meanings of the term gradual typing nowadays. So one is basically, any type system that allows some amount of dynamic code in your language. And then there's this other, which is follows the discipline of the house Sikh, right? Yeah, I am a pupil. So I'm going to be talking about this work that was initiated by Jeremy in 2006 with Walid Taha, and had led to the name Gradual Typing. Conveniently, this was the paper, and it appeared at Scheme 2006, which is another way of saying that it was rejected from ICFP 2006. Nonetheless, it has more citations than any paper I've ever written. So for those of you whose papers were rejected and showed up, this could be you 10 years from now, or 12. I guess you need 12. So let me tell you what gradual typing is about. It's to say, I talked a little bit about this in PLMW yesterday, so the students can sleep if you were out partying last night for a little bit. But you have this idea of a mixed language where in blue we have the statically typed language, and then in red we have the dynamic language, so just making things concrete. Now, if you look at these right now, you might say, what's the difference? They look exactly the same except you change the color. Well, yeah, I mean, a lot of times you'll hear people in gradual typing say, oh, you add type annotations and that makes it gradual. And well, there's this thing called type inference, and you might actually infer the types. So it's the visual presence of types is not really what makes the distinction. The distinction is the language boundary and the decision of which interpretation am I giving to my particular syntax. So given a program that links static and dynamic, we expect some amount of static enforcement, where if there's a conflict in the static language, you'll get an error right away, and that really corresponds to our type discipline. Our rich type discipline is protecting us statically. But at times, because of this conflict between dynamic and static, you may have situations where this protection comes into play, and you end up with a runtime type error as a result of conflict between the two type disciplines. So this is the heart of gradual typing. And the way it's realized is by creating something altogether new. So what you have is something that's called a gradual language, and the gradual language has its own typing judgment. And this paper by Jeremy and Michael and Matteo and John Boylan talks about, well, what are the criteria for a language that is supposed to be called gradual? What do we mean when we say gradual language in house Sikh? So given a language like this, I'm not going to talk to you about the criteria yet. Well, actually, I guess I'm directly talking to you about the criteria, which is to say, one of them is that you have your static and dynamic language, and you better be able to directly inject your static language into the gradual language, which is to say that every static program is a gradual program and has to try and preserve the invariance of the static language, the meaning of the types, without change to the syntax even, really. On the other side of the dial, your dynamic language also is a gradual language, but it's typically injected by a compositional translation that turns your syntax for dynamic programs into messier gradual programs that kind of make it clearer to you that there's some distance between the static language and the dynamic language. And given that those two things exist, you also want to be able to take mixed programs, translate each component of those programs according to the regimes on both ends, and then finally have to somehow talk about what happens at the edges between the two languages. So you can think of the gradual language in this context as like the CLR. You have this common language runtime that allows you to link two different languages together in a safe way that protects one from the other using dynamic checking. And it turns out the key to getting this linking to work out safely is that it's the type structure of the gradual language that determines what appropriate linking is. When is it okay? When is it not? So under the hood, this is a simple example of gradual typing, like what you would have seen in the original Seek and Taha paper. You have your static type language, and I'd already said that the statically typed language has to every statically typed program has to be a gradually typed program. So we extend the language with gradual types, and then all the static types are gradual types, and you add this question mark. And the question mark is this, as I like to pronounce it, because it's the unknown type, and it captures this idea like, I really have no idea what the type information is at this point. I couldn't tell you, don't know. And that turns out to be a different thing from, say, type inference, where I have a variable and it represents something very specific. I'm saying this really doesn't represent something specific. It's like we're turning our types from points into types as clouds. And using this unknown type, it kind of induces a notion of like static type information ordering that's often called precision on your types, just independent of anything else. So at the top you have like the least information, I have no idea what's here, and then at the leafs you have your static types. So all of your static types are at the leafs of the precision relationship, and then everything goes up in order of losing information. At first, it might seem kind of similar to subtyping, but notice that the domains types, they vary covariantly, not contravariantly. So it's definitely, we're not talking about safe substitution. We're talking about information content, which is semantically a different thing. So somehow we have to blend this notion of precision into our typical static type system to lose information. And the idea that was originally initiated by Sofia Dressapoulou and Matt Anderson in a paper about blending JavaScript and Java, but was taken to the level of structural typing by Jeremy and Walid is gradual type consistency. And you can define it pretty nicely using a kind of this two-dimensional diagram, which basically says that two gradual types are consistent with one another as long as you can pull them down to two specific types that happen to be equal to one another. So it's like, oh, like it could possibly be equal. Something in my realm of noise actually overlaps. And this is not the original formulation in a paper. It's taken kind of years to figure this out, sadly. But that's how research goes. So there's some interesting properties of this definition that I gave you, and one of them is that it really does preserve our notion of type equality. So if I have two types that are equal, they're definitely going to be consistent. And if I have two static types that are not equal, they're definitely not going to be consistent. And I sort of never ask about equality over here on the gradual type side. I'm only wondering about consistency. That's really the main question that I want to know, whereas type equality is just type equality as we know and love it. So there are these additions now because we are talking about this conservative extension. So in this particular case, the thing on the left, yeah, might be a bool in the domain. The thing on the right, yeah, might be a bool in the codomain. So yeah, they could be equal with one another. So they're consistent with one another. And this idea transfers over to other relationships between types. So if you have a language with static subtyping, you just plug static subtyping into the bottom of your two-dimensional diagram, and you get something that pops out the top called consistent typing, which appeared in the second paper that Seek and Taha wrote about gradual typing to explain that no, gradual typing is not subtyping. And no, it's not, because that thing is definitely not subtyping, and I'll show you in a second. So if you look at consistent lifting, you'll find quickly that yes, it has all of the properties that you expect of static subtyping. All of these are static types, and I'm using the top symbol for like a top type, like the universal supertype. But notice that question mark and top don't behave like one another. Question mark is both above and below consistent subtyping, whereas top is definitely not below int. So there's something fundamentally different going on with this loss of, like, static subtyping up to information content of my types. So then what's typically done is you take your static type system and you lift the rules so that your old linking structure, the relations like equality, which tell you when you might be able to connect two things together, become consistency. So we've replaced like perfect linking with this sort of approximate linking, where plus is a linking structure for things that are integers. And then finally, we take the knowledge that we learn from statically type checking our language, and we translate it into this instrumentation language, which is often called a cast calculus, which kind of reifies those places where the information content was not sufficient to guarantee definite equality, but had to settle for merely consistent. And we have to check that later because we don't have enough information yet to do that. This is where the runtime checking comes in. So that's why I really like to say the question mark is the unknown type, and it just happens to induce dynamic checking. It's not a dynamic type, because types don't run. They're properties of programs. So it's not saying like, yes, my program is dynamic. So now, stepping back a second to this idea of the common language runtime that rules both static and dynamic and mixed, you know, compared to the JVM or the CLI, you know, it's not that bad to program in. All I did was add a type to the type system, right? It's just a question mark in my static type system. So really, the gradual language also works as a surface language. People are perfectly happy to program in it directly instead of programming in a dynamic language. And you may want to write a program that's basically all static and then just use a very fine-grained amount of dynamism. And the gradual language is a fine place to do that. And in fact, much of the literature on gradual typing is written from this point of view, focused on the idea that we'll use the gradual language directly without noticing that this is not the same thing as the dynamic language. It actually gives you more errors if you directly inject a dynamic program in rather than do the compositional translation. But the translation already appears in the original paper, but the focus has been more on gradual as the language that I want to program in. It's useful to have all three. Now, once you're in the gradual world, there's this set of properties that talks about what's the relationship not just between fully static and fully dynamic, but what happens in the middle, especially when you're thinking about this fine-grained dynamism. And so Jeremy and his colleague came up with these refined criteria, which include these two that are called the static and dynamic gradual guarantee. And the way I like to think about these is that you are now allowed to kind of continuously deform your program between static and dynamic. And really, the result of doing that by varying your question marks, like add more question marks, needs more question marks, and doing that should only change the static and dynamic type errors. It shouldn't suddenly cause your program to send rude emails to your mother or launch the missiles, as people like to say. Or like start the dance party would be cool, but you still don't want your program to do it unless you're ready. So the result of this kind of composition of features ends up being a very robust theoretical framework that's been pretty useful. Like there's the first paper that said like, yeah, we can do this. Gradual typing makes sense. And then the second which says, and it's not subtyping. And the third that says, and it's not type inference. And there's another paper that goes even further by Eric Tonter and his student that says, like, let's go from simple types to adding subset style refinement types in the flavor of liquid Haskell. And then there's some work by myself and my student and Eric, Felipe is my student, Bañados, and then Eric and I were also on board, and this was on doing type and effect systems, where now your type system doesn't just talk about what the shape of values are, but it talks about what kind of computational effects you can do while you're evaluating an expression. And that makes things a bit more complicated to think about. And while I wasn't at this point then, I now realize that what I really wanted to think about is what's the semantics of my types. In fact, what I would say is this was the paper that led me to start thinking about the semantics of my types, because we built a static type and effect system, and we proved type safety, and the thing was a big lie. It was like, no, you can't mutate memory, and you could mutate away all you wanted because we didn't know what we were doing. And so the trick was like, how do I sort of attack my system and say like, no, it really does have an attack model that it's preventing, is what your type system is doing, and you can trust that certain things are going right. And we were caught up in progress and preservation and just didn't understand that hiding underneath at the end of that page of Wright and Felison was the fact that there's semantics hiding in the type safety proof, and we didn't understand it. And then recently, Matthias Toro, who's a student of Eric's, and then Eric and myself worked on a paper that's going to appear soon about going from a simple system to information flow security typing, which is about making sure that certain kinds of values don't leak out of certain kinds of parts of a program. But in this particular case, the notion of type soundness really allows us to think about program fragments, where I can have a piece of code and I can have a security type on it, and I can know absolutely nothing about how the body's implemented, and I can know absolutely nothing about the context, but I know something, like if it's a function, I know something about how the arguments will ever be mixed with one another, even though it's a gradual system, where it could be that this is the only static type annotation in the entire program, and the rest of the thing is dynamic. Turns out that's really powerful, because what you now have is you have a dynamic language with a really cool runtime assert mechanism for security properties. So this can help you design dynamic languages with interesting properties. An example of that was done differently was by Cormac Flanagan and John McCarthy on temporal contracts, where what if I had contracts in my racket system that could talk about time flow? And you can think of that as it's really a type property, and maybe that could be a type in a type system and a contract in a dynamic language with the same meaning. That's kind of the strength of the framework. But I haven't done that, so somebody go write the paper before I do. I'm lazy, I'll wait until you do it. And there's much more. There's many other things that you can do. So historically, developing these dynamics, the static system has been turned out to be almost like just arrived almost nearly perfect on day one. But as Jeremy noted, and I got to tag along, really is how I'd say it, it's like, given the name gradual typing, you think the most interesting aspect is the type system, but the dynamics are really the interesting part. It's turned out to take a lot of work to figure out how do I build an instrumentation language and what properties should it have. The refined criteria were part of attacking that problem. So Robbie mentioned this already, but Eric and myself and Allison, a student of mine, worked on this piece of work called Abstracting Gradual Typing, and the idea was, roughly speaking, like, let type safety whisper in your ear, as I describe, and using that you can systematically kind of churn out from your static type safety argument a dynamic semantics and a gradual type system that satisfy the properties that Jeremy was looking for. And it kind of gives you guidance in designing a programming language. It's not the end of all ends, but it's at least some tool to give us a handle so that we're not just like shining our flashlights in the dark trying to design languages that will satisfy particular type guarantees, that will respect particular type guarantees. And it's turned out that tool has been really useful. We've been able to, without it, I would say there's some of these that I really plain couldn't have done without having this framework. It took more work afterwards. It doesn't do all the work for you, but it really got us close enough that we could pinpoint the pain points and get much more work done on building gradual type systems. So I want to now talk a little bit about some strands and some related works. So gradual typing, this paper came out in 2006, and as you can imagine, people had been thinking about combining and trying to combine static and dynamic checking well before 2006. I think it's Don Knuth has this saying, which is like, you know, sometimes people forget that back in the 1970s, we had some pretty good ideas. Which is part of why I love reading old papers. I feel like I find things that are a little bit forgotten. One of the things I love about the Milner paper is that we sort of, it's hard to keep abreast of everything, and we have limited time, but occasionally dipping into the past is a nice way of getting insights that weren't available back then in reference to what's been done since. And you can kind of transport some great ideas forward. But before I go forward, I want to go sideways. In the same year as the gradual typing paper came out, Sam Tobin-Hochstadt and Matthias Felleisen wrote this paper on interlanguage migration, which in essence was describing the problem that I described at the beginning of the talk. And this is really the gestation of the typed racket project in particular, led to that, which led to Sam's PhD and a lot of neat work in it. And both of these are very complementary, and in my view, the goals really match up really well, even if some of the perspectives are slightly different, so it's hard to see it when you read the papers. But there's partly a good reason for that, which is this work and this line of work is doing something that is sort of harder than the thing it really is harder than the thing I describe. And in like private communications, I typically refer to some of it as like Sam's problem, which is the way to say, like, I will have no part in that, that's way too hard. Let's let Sam do it, he's smarter. And the part of that I find really fascinating is what I'd call type system anthropology, where what they're trying to do is figure out, like, we've got a large code base in a dynamic language, and programmers aren't stupid. They have some sorts of reasoning facilities in their brains, and what we want to do is turn those intuitions into a system of modular reasoning about programs for some notion of modular. And so this is really super creative, super hard. It's like it really is doing empirical science in a way. How do I build a model of how people reason about programs and then mechanize it? I'd say that this is exactly the same thing that Frank and his students were doing when they were going from refinement types, from SML types to refinement types, which is to say, yeah, people somehow can successfully use these crazy non-exhaustive matches. What kinds of reasoning principles are they using so that we can kind of formalize them and mechanize them? Then, just because Sam and Matthias are ambitious, they're like, we also want to mix the two things together. So they're trying to solve both problems at the same time. Like, not only do I want to create a new system for reasoning about programs, but I also want to be able to blend my old reasoning with my new in a sound way. So in that sense, they're tackling Khurram and Joshua's problem in the same world, and using mechanisms that mostly work with the idea of the mixed language directly rather than thinking about translating it to a common language runtime. Luckily, they have this amazing language-oriented design framework called Racket, which has this useful feature called contracts that were developed by some guy. Schmindler, Bindler, I don't know, whatever. So this project's been going on for quite a while, and there's this really nice retrospective paper that talks about the work in typed racket, but even, I think, more valuable, a backwards look at what happened before it and all of the efforts to try and, many efforts, maybe not all, to try and combine static and dynamic checking and some of the things that went wrong with them. So if you're interested in this area, I think this is absolutely a must-read. And going forward, it turns out that they're still at it. So Ben Greenman and Matthias will have a talk in the Gradual Typing, we won't talk about whatever the rest of that is, Gradual Typing session, which will be on Wednesday, where I don't want to spoil it for them, but there'll be some really interesting stuff about thinking about what you get from various kinds of strategies for interpreting migrating types across these barriers. So now, stepping backwards, we have this classic work that's really interesting called soft typing, and this was Corky Cartwright and Mike Fagan, and then Andrew Wright, who's the same Wright from the Wright and Felleisen Progress and Preservation, well, syntactic type safety paper. And what they were trying to do was basically use/extend Hindley-Milner type inference as a means to migrate dynamic programs. And I think they were mostly focused on performance, getting rid of dynamic checks, but they were trying to think of like types as the means to make things work. And this worked more or less. At least a couple of theses came out of it, but the ideas in there are really interesting. And it was in the air at Rice that a bunch of other people would kind of work in the same space. So Matthias, of course, it's like Matthias did everything in this talk except Jeremy's stuff, which is everything. So Matthias and Cormac were working on this thing called set-based analysis, which I would roughly describe as not typey in a way. It was much more based on, it's much more similar to abstract interpretation, but I'd say that's a qualitative thing. You could argue, it's arguably this is also types, but it is definitely an analysis mechanism. One of the interesting things about this was that the paper on top seemed to produce things that were precise information about errors especially, but really bad performance because it had to do this sort of whole program analysis, whereas the lower one was attempting to recognize this idea that we need modular and compositional reasoning, but it was having trouble getting enough precise information to achieve what was done on the top. That's my understanding of the work and its legacy. It's useful to point out that the person on the bottom is what happens if you take Sriram Krishnamurthy, Stephanie Weirich, and Matthew Flatt and kind of merge them into a super researcher. So this person down here, spends their time researching how to teach the youth to write compilers for dependently typed languages. Wait a second, I could swear that my department just hired someone who's supposed to do that. Well, competition's good, but in any case, I'm pretty sure that William's looking for students since he's starting up as new faculty at UBC, so welcome, William. So I talked a bit about this idea of using some sort of inference or analysis to migrate languages, and this has kind of come back in the context of gradual languages where you say, assume I have a gradual language already, and then let's exploit the structure of gradual typing to help migrate along the gradual spectrum instead of sort of an arbitrary way. So we now have a framework in which to apply this idea of inference. And so one nice piece of work that I really like the ideas in is this work by Avik Chaudhry and Asim Rastogi and Basil Homer on migrating. And then even more recently, there's some work done by the sort of Oregon State Goon Squad, and they're not Matthias, it's really something, and it's not Jeremy, but on migrating gradual types. And this is really neat because what they're doing is they're using type inference to help migrate to a language where the static language has type inference. So it's like, ooh, like inference all the way down. And then at the ICFP, they'll kind of continue this trend with some work on evaluating cost models of migration for gradual typing, because there's recent work that says that it's the performance of these programs that are in the middle and not at the edges can be really challenging. And this is an open, pragmatic research project. And I'd be totally remiss to leave out this paper, Dynamic Typing, Syntax and Proof Theory by Fritz Hengelin. I mean, this is one of those papers that you sort of put under your pillow and hope that like the ink will seep into your brain at night. And you read it over and over again, and it's like, it's a crazy gold mine of ideas. And it's had substantial influence on a lot of papers in gradual typing, including ones that I've written. And I think some of the papers I write are really like, what is Fritz doing? And I'm like, I think he's doing this. And then you're like, wait, there's more. Oh, he's doing this. And like, wait, no, there's more. No, he's doing this. And so like, it's kind of like we're working on the definitive translation of this Homeric epic called Dynamic Typing, Syntax and Semantics. And the tradition continues, which is to say there's this really nice paper by Max New and Amal Ahmed, which has really tight connections to a lot of the work that you'll find in Fritz's paper and sheds new light based on just a different perspective. So that's our strand of related work. That's my perspective from up on high at UBC in Vancouver of gradual typing. And before I end, I think it's really useful to take some time just to be grateful about so much that we have going for us and the people who've helped us get there. So I'll start with the hardest, which is at PLMW, I explained that I had 2 degrees in electrical engineering before I got to computer science, even though I kind of hated electrical engineering. So this is my stepdad, or my other dad, who was an electrical engineer. And he was just so amazing that I wanted to be like him, so I studied electrical engineering. And it didn't work out for me. I was more of a software person than a hardware person, but he was okay with that all along, always cheered for me. And unfortunately, he succumbed to cancer in March. And I miss him greatly, but I like to think that, and I like to hope that he lives on in me and all the people that he influenced. So as my mother says, I was not an easy child to raise. So you think this is being a smart aleck, you should have seen me at 12. So even academically, it really took a village to kind of make me the person I am. So I have to thank my advisor, Andy Lumsdain, especially for always believing in me, even when I didn't believe in myself, and letting me persist. I have to thank Dan Friedman for getting me addicted to programming languages. I mean, he's a fantastic pusher. He's like, the first interpreter's free, and then you'll have to defunctionalize your own continuations after that. Amar Sabri, who was on my committee but not my advisor, would very patiently sit and listen to my harebrained comments and kind of one by one pluck the hairs out of it until it turned out to be kind of a smart idea. And it was really great to learn how to think about programming languages through his perspective. And I did a postdoc with Frank. And I mean, the main thing to say about him is just that he's really inspiring. And so I'm grateful. And I can't help but have massive amounts of gratitude towards Jeremy Seek and Eric Taunter. I've known Jeremy for more than half of my life, and he convinced me to learn C++. Whether that's a good idea or not, you be the judge. But it's just been really a joy to get to be friends and very intimate with Jeremy and to do lots of cool research with him. And Eric just like super excited, tracked me down one day, and then we just hit it off. And I mean, we've just really, done a lot of great stuff together. I think when this music video drops, the internet's going to light up. But in the meantime, you'll just have to settle for the papers that we get to write together. And we have super lots of fun. And among both of them, I really look forward to growing more gray hairs as we write papers together. And then last, I'd really have to thank the students that I've gotten to work with over the years. I learn a ton from them, and for some reason they keep thinking that they're learning something from me when I'm just like sucking the blood out of them so that I can stay young. So thanks, y'all. Oops, some of them are here, damn it. So that's the conclusion of my talk. And I'll just leave you with this kind of image of really the framework that I think gradual typing sets up in a lot of the pieces. I hope you got a few things out of the talk, and I'm happy to take questions. Thank you.
Thanks, Ron, for a fantastic talk. I have the question. Which one you want? You like any of them?
Oh, how about you give them to me?
Yeah. All right. So here's one that seems particularly well liked by the audience. I'd like to use dynamic Haskell programs from Agda. What do I do about non-termination?
That's a great question. Really great question.
I'm glad I'm asking it.
Yeah. Maybe I should answer it. So I've thought about this just a bit, which is really interesting. And once again, I really think this boils down to semantics of types, which is to say, if you take the simply typed lambda calculus, and I'm stealing this basic example from Eric Taunter because he's the creative guy. So if you take the simply typed lambda calculus, you can use a semantic model to prove that it always terminates. But if you lift it to if you go into the gradually typed lambda calculus, it's no longer a terminating language because it completely contains the dynamic language. So if your semantic concern is termination, you somehow have to wire your mask to be able to protect the part of your program that needs termination to happen, which means somehow if it can't be sure that a dynamic program is going to terminate, it should error out, basically. You don't just kind of keep going forever. And so I really think it ends up being an issue of what are the semantics of my types and what kind of runtime enforcement do I have to guarantee that that behavior is preserved.
All right. Alejandro asks, if you have types representing effects, what's the intuition behind consistency? Do you have to match exactly the effects? Should there be a subset of them?
Okay. Read Felipe's paper. But really, this was like the thing that really was the thing that led us to building AGT ultimately, which was to say, we decided, hey, let's do type and effects. What the hell, consistency? Like, we just started throwing things at the wall. They kept sliding down. My wall was getting dirtier. And Felipe kept working at it. And then at some point, we started to see a pattern in what we thought was going on. And what roughly happens is your effects can be like a set. So you have this notion of set containment. And then you say, like, what if I add the idea of a set that has some definite stuff and then maybe more? And you end up with a kind of idea of a consistent effect set, which might represent more effects or less effects, and then just roll from that.
This one's a little bit more open-ended, so I'll let you try run with this one.
Okay.
Does the complexity of the gradual language, I think the combination of some type systems, depend on the distance between the languages, or is it somehow more tied to the complexity, the maximal complexity that there is in the languages, or the type systems that you're trying to combine?
Oh, that's a really interesting question. So the way I would try to answer that is, like, in my experience so far, where does the complexity come from? I would say that the complexity so far that I've seen comes from the nature of the properties that you're trying to preserve, and especially your more static language. Because I haven't done particularly sophisticated properties in the dynamic. It's mostly just been simple types, because it's kind of about as far as they've gotten. But to give you two examples, the community has been bashing its head in the face trying to figure out how to deal with parametricity forever. Oh yeah, Robbie got into this game for a bit and then stepped out. So people are like, what is this supposed to be? And parametricity is hard because it's a property of multiple runs of a program. It's not a property of one run of a program. In a certain, like, if you characterize it at its Platonic ideal, it's about multiple runs of a program. And how are you supposed to do something about that with one run of a program? And a lot of complexity, at least in design, if not in the machinery, comes from that. And my experience with Eric and Matthias on doing information flow security had the same thing, that it's about multiple runs of a program. And so the sophistication of your type properties definitely affects the sophistication of the checks. As far as the distance, I'm a little less sure. The most I have is Felipe's master's thesis was about, his ICFP paper was about just going from simple types to effects, and his master's thesis was about going all the way from the unknown type to type and effect system, so being able to go kind of both ways. And so we already had one part of that and then did the other. And the complexity did grow because he actually has all three stops. And it seemed like there are times when you need some bits in the middle in order to make the run all the way to the end happen.
All right. Thank you very much, Ron. And let's go have some coffee.